Hello and welcome back. If you're new here, my name is Eugene. I am going through the math in Mark Spitznagel's book on investing called Safe Haven. I've made a whole bunch of videos on it before, so you need to watch those before you watch this one if you want to understand what's going on. I thought what I would do a few months ago was learn Python so that I could double check what was happening in terms of the math behind all of these probability charts that are in his book. And so there were three main dice games whose math I wanted to check. The first one was the Nietzschean dice game where you are rolling 300 times and you wanted to see the possibilities from 10,000 outcomes. And you're betting your entire net worth on each of the dice rolls. The second dice game is the one where you only bet 40% of your net worth on each dice roll, and then you combine it with the 60% that you save in cash. And then the last dice roll is the one where you are betting 91% of your net worth and you're saving 9% for insurance, which might blow up. So if you want to get an understanding of those three dice games, please check out my past videos. This is meant only for people who have gone through those videos already or who have read the book. So I wanted to double check the math because I was worried that he might have something different from me or from others. And I'm glad I did, because I ended up finding that what he wrote in the book was not what would come out of this program. So I'm glad I double checked it. So if you don't know how to code, you should still be able to watch this and follow along and understand it. So let's get started. This is the first dice game where we are betting our entire net worth on each dice roll. So the way that I set this up is that there are two functions. And there's also this list here, which I call dice. And instead of writing 1, 2, 3, 4, 5, 6, I wrote 0.5, 1.5, and 1.05 4 times so that it would save me an extra step. So let's go into the first function, which is basically like the first program that I'm telling the computer to do. What it does is it takes whatever wager number you would like and it multiplies it by one of these numbers. It picks a number here at random and then it multiplies it by that. And then that becomes the new wager. And then it picks a number from here again and it multiplies that by the wager and then redefines the wager to be that new number. And then it does that 300 times. So that's what these two lines mean. And that is to simulate what would happen if you were to roll a dice and play with your net worth for 300 dice rolls. This last line here, what this does is it lists what the end wealth is after every time this little function runs. So for example, because we don't just want to do this 300 dice roll game once, Spitznagel does it 10,000 times. So at every end of the 10,000 rolls, I basically jot down what the end wealth is in this pathway list here. So that's what this first function does. What the second function here does is it runs the first function 50,000 times. You can change that to 10,000 times like what Spitznagel does, but the more you run this function, the more accurate your end wealth will be and your end numbers. So that's what we're going for here. Basically says run this function as many times as is written here. I've written 50,000 because I find that let's do 500,000, heck. That gives me the best accuracy. So those are the two functions. And then this stuff here, what this does is it calls this function and you just need to type into this space here how much your starting wealth you would like it to be. So I put a starting wealth of 1 because in the book that is what Spitznagel puts, and I run I ran this 500,000 times, so I put 500,000 here. You don't need to change anything in here if you are playing with this at home. You don't need to change anything in here, and you don't need to change anything in here. So that's that. Now these lines here, what this will basically tell you is what the arithmetic average is of pathway. So in other words, the arithmetic average of all of the outcomes from all of the games that have been happening for 500,000 times. So that's what happens here. Same thing, geometric average of pathway, geometric average of all of the 500,000 rolls, and the median of all of the 500,000 rolls. And then this will also tell you the 5th percentile. Okay, so when you run that, this is what happens if you start out with a wealth of $1 and you play 300 dice games and you play 300 dice games 500,000 times. What you find is that your arithmetic average is 10,534, which is expected, but your median average is 0.0095, and your geometric average is 0.0095, and your median is 0.01. And so what that means is, if I'm correct, I found that the geometric average isn't calculated properly for some reason here, but let's look at the median. What this would say is that you would grow by, you wouldn't grow, you would shrink. You end up having 1 cent at the end. So if you were to start with $1, you would end up with 1 cent, and that is the median, which means that 50% of all of the other outcomes are outcomes where you have less than 1 cent. And if you look at the 5th percentile here, you see that it's like 7 to the power of -7, which means that it's 0.00007, and that is the worst, one of the worst outcomes you can have. So basically, this game tells you that you shouldn't do that. But what I found interesting, was that when you look at his book, he says that the Bernoulli expected value is 0.985, or a -1.5 compound rate. And the median is somewhere between 0 and 1 as well. But if you look at the computer program, you find that the geometric average is not 0.985, it's actually 0.09. So, just to be safe, because this is a randomness thing, we can rerun this program, but it looks like, for some reason, my math or Spitznagel's math isn't turning out to be realistic when you look at the possibilities. Yeah. So it takes a bit of time because 500,000 rolls it takes a while. Yeah, so once again, it's 0.009 and 0.01. If we were to get the same numbers as Spitznagel, then that should be closer to, it would be 0.985 for the geometric average. So I'm not sure why the numbers aren't matching up with his. So that's the first dice game. The second dice game works very similarly. You also have two functions. The second function is identical. You just run the first function 500,000 times. The first function, though, is a bit different in that instead of just betting your entire wager every dice roll, you're only betting 40% of your dice roll. And so what this basically does is first it separates 40% of your wager and 60% of your wager, and then it multiplies the 40% by a random side from the dice, or sorry, a random side number from here, and then it adds the 60% that's remaining. And then it redefines the wager as the sum of these two parts. And then it does that 300 times. And then if it goes through this once, it will add whatever the end result is to pathway, over here. And then the second function runs this first part 500,000 times. So this is for the 40-60 split. Let's see what we end up getting for both a geometric average as well as a median. In the book, I believe that Spitznagel says that your geometric average is very close. It's going to be very close to your median. So it's reliable in that sense. So in the book, I'm on page 78, he says that the geometric average should be 0.6%. That's the rate of growth when you split things up like that. But if you look here, we find that the geometric average is 6. It's close. So, which is not what I was expecting, because in the book he says 0.6. Here the math comes out as 6.8, 6.9. So I guess that's a bit heartening, because it means that if you start out with $1, then you're going to end up with $6, $6.8 or $6.9 in the end. But once again, the end result is not what we expected from the book. And so that's a bit annoying. So we'll just run it one more time just to double check, and then we will go to the third one, which is the insurance payoff. This time I wanted to look at the 5th percentile because he mentions that too. And the 5th percentile is relevant because when you're looking at how much you should be splitting things up, what you're seeing is like the worst possible outcomes, and the 5th percentile shows you some of the worst possible outcomes that could happen. So here we see some of the worst possible outcomes is that it becomes 0. You start out with $1 and you end up with 23 cents, which is a lot better than the last game where you ended up with $0.000007, but it's still, you're losing 3/4 of your wealth. So now we go to the last one, the insurance payoff. And once again, there are two functions. This one where it has 500,000 runs of the first one, and then this one is you take one of these numbers and you split it up into two parts. The first part is 91% of your wager, and if the dice roll is 0.5, if you roll a 1, then you're going to add that 9% multiplied by 5. If it's not 0.5, so if you roll anything other than a 1, then you just don't consider that a part of the wager, and you just ignore it. And then once again, you add the end wealth to your this list here. So we're going to run that, and we're going to see what the end result is and what the 5th percentile is for the geometric average and for the median. In the book, I'm at page 88, and the geometric average according to the book is 2.1%. So, yeah, 2.1% geometric average. And the computer says that the geometric average here is 4.34. The median is 4.15. And very surprisingly, the 5th percentile is 0.09. So this was less than the 0.23 or the 23 cents that we had. Now you're only getting 9 cents. And this was very shocking because what it suggests is that this insurance payout actually pays you less than the 40-60 split. And that is not what Spitznagel is saying in the book. He said that the insurance split or insurance payout would pay you more than the 40-60 split. So I have no idea what is actually going on. I don't understand why my Python code is giving me numbers that are different from Spitznagel. I don't understand why the 40-60 split is preferred according to this coding stuff that I've done. So if you spotted a mistake in either my math or my thought process or in the code, and so that please leave a comment below and let me know. Or if you think that I was actually right and Spitznagel perhaps made a mistake, then please let me know as well by commenting. Thank you.